everybody. Hope you're doing well. We'll talk about something new. And the question comes up is, how can you find the derivative of something that looks like this? Okay, we know how to take the derivative of square roots. Remember what we did with square roots? Like if you just have, for example, y is equal to the square root of x, what we did is we rewrite, and there's so many functions that you have to rewrite before you take the derivative, but this is one of them. And then we use the power rule. Right? So it'd be y primed is equal to 1/2 x, and then you have to do 1/2 minus 1. Always subtract 1 from the exponent when you use the power rule, and that would be to the negative 1/2. And then you would simplify it by rewriting this as 1/2x to the positive 1/2, and then finally y primed is equal to 1/2 square root of x, if you rewrite it in radical form. But now we have more than that. Clearly we have another function inside that square root. And y'all know these are composition functions. We have composed the square root of x and x squared minus 6, a polynomial, together to create a brand new function. And so there's a rule for taking the derivatives of things that look like this. And so this brings me to just that. We need a rule to handle composite functions. And we have one, of course, as you expect. It's called the chain rule. And here's the setup, and then we'll prove it. So the chain rule, if you have y equals f of u, just some function that has a function inside of it, and u is equal to g of x. So another way to say that would be f of g of x, like we have here below. Now a couple of things are important. The f function, which I call the outside function. I'm going to go ahead and start using that idea. The f function is the outside function. The g of x function is the inside function. I use that so much, I want you to be familiar with that. So notice how g of x is on the inside, f of x is, or f is on the outside. If you have that situation, which we do above, by the way, the inside function here is the polynomial x squared minus 6x, and the outside function is the square root of x. Okay, so back to our theorem. If you want to take the derivative of your function y with respect to x, and y is the composite function, then you take the derivative of y with respect to u times du over dx. Now, to me, that's better expressed the second way that it has it written here. The derivative of your composite function is the derivative of the outside, rewrite the inside, times the derivative of the inside. So we want to take a look at this proof. There are actually two cases to this proof. The first case is the one we're going to look at, where g of x is not equal to g of c. I'll show you why that has to be done when we do the proof. And then there's this special weird case where at certain values g of x equals to g of c. We're actually not going to touch that one. That shows up in the appendix in your book if you are willing to look at it, but I think it's kind of beyond the scope of what I need to make you suffer through as we're doing this. So let's go through the proof. First thing, we're going to use the alternate form of a derivative. Remember using that when we took the derivative of an absolute value function? What was required to use that for a problem is we needed to know what c is. We had to have a specific c value, but it works great for this proof, so we're going to stick with it. Okay, so there is your alternative form already plugged in. So h primed of c is f of g of x minus f of g of c over x minus c. Now, here's what we're going to do. We're going to multiply this definition of a derivative by, remember we call this a unity fraction? This is just equal to 1. It's a glorified 1. G of x minus g of c over g of x minus g of c. That's completely okay to do, right? Even inside the limit, because the limit as x goes to c of that value is 1. All right, so here we go. What are we going to do next? We're going to switch denominators. Seems like a weird thing to do. So I'm going to put this g of x minus g of c on the left side and x minus c on the right side. Now, is that okay? Why are you really allowed to pull a stunt like that? Notice the numerators stayed exactly the way they are. Well, it's because when you multiply fractions, You know, you multiply numerator times numerator and denominator times denominator. We know that. And we have the commutative property of multiplication that says you can multiply in any order you need to. And so switching those denominators is perfectly fine. So where does that take us? Okay, well, let's use the product rule for limits. When I say product rule, I probably should be more specific and say product rule for limits, because I'm going to split this up into two separate limits. So we have the limit as x goes to c of our first fraction times the limit as x goes to c of our second fraction. Now, if you take a look at this, remember our alternate form of a derivative above. Okay, this f of g of x minus f of g of c over x of g of x minus g of c. Okay, that is the derivative of f of g of c, right? Does that make sense? Now, it's not what we started with, okay, but you're subtracting those inside values times this is another alternate form of a derivative, and this is going to be the derivative of f of g of c. I said that wrong. I just mean of g of c. There's no f in this side. So that brings me to the next line. Look at there. So f primed of g of c. This is the derivative of f with g of c on the inside. And then this is the alternate form of a derivative of g of x. Again, g primed of c. Okay? And that proves it. That's it. That's what we were trying to get. Now, that's true for c, but this is the alternate form of derivative, which also proves it for x. Again, you got this weird special case. What if g of x equals to g of c? But we're not going to worry about that weird situation. This is enough that we'll feel comfortable using it. And if you're curious, I do believe it's in the appendix section of your textbook. Now, I am far more interested that you know how to use the derivative. And you've got to be able to recognize when you have composite functions, the inside part and the outside part. May be very clear for a lot of you, but I just want to make sure we've got this clear. So in the first function that we have here, y equals 5x minus 3 all to the 5th power, the inside part is the 5x minus 3. And that's what you would call your u. And the outside part, if you write that as a function, it's the 5th exponent. But you could write that as x to the 5th. Or that would be like, I guess it'd be more specific to say that's u to the 5th. But again, the outside part is the exponent, the inside part is 5x minus 3. Okay? Now, on the next function, okay, we have an outside part and an inside part. Now, keep in mind, when you pick these, there are different ways to pick them. Like when I'm looking at this function, you think, well, is the inside part x plus 1, or is the inside part the square root of x plus 1? What I want you to think about is you've got to be able to take the derivative of each. So you need a rule to find the derivative of each. And if we let u equal the inside part, which is x plus 1, we definitely know how to take the derivative of that. What if we let the outside part be 1 over the square root of u? We know how to take the derivative of that too. We could use the power rule, right? We could rewrite this as u to the negative 1/2. Because the square root is the 1/2 part. You take it to the top, it's u to the negative 1/2. As long as you can take the derivative of each of those parts, then you've got this. You've got it figured out. All right, so here we go again. Outside part, inside part. Keep in mind, you've got to be able to take the derivative of the inside part. You've got to be able to take the derivative of the outside part. So if we let the inside part be, we call it u, is pi x squared. Do we know how to take the derivative of that? Sure we do. That's the power rule, right? Where pi is just a constant multiple. Okay? The outside part is your 3 tangent of u. Do we know how to take the derivative of that? Of course we do, right? We've got we memorized it in the last video, right? That the derivative of tangent of x is secant squared of x. Of course, this is a u, so you would just change it. And that 3 right there is a constant multiple. So we're doing good. We've got this. Okay. What about cosecant to the 3rd of x? Now, here's what I want you to think about. I'm going to write this at the bottom. cosecant to the third of x really is cosecant of x to the third. You really have to think about that when you see that notation, that third in the middle means the whole thing is to the third. So that may change your thoughts on your outside and your inside. Your inside is u is equal to cosecant of x. Your outside is this u to the third business. And you do know how to take the derivative of each of those. Remember, the derivative of the cos is negative. So it's going to be negative cosecant of x, cotangent of x. Okay? And we know how to take the derivative of u to the third. It's power rule. And then the last one, let's look at purple. The inside part would be u is equal to 5x over 2, and the outside part would be the sine. So sine of u. That one was actually easier than the two above it. So we're going to use this. We haven't taken a derivative yet. We're going to use this to help us work lots of problems. Practice is key here, folks. All right, so we have our first problem. I've got it labeled as B, so maybe we have our second problem. Anyway, so we've got 3x squared minus 4 to the second power. So keep in mind, you got to remember what's the outside function, what's the inside function. And so the rule, remember, is you take the derivative of the outside. I'm going to write this down. Derivative of the outside. Then you rewrite the inside. And then times, big dot for times, the derivative of the inside. Okay, so that's the derivative of the inside. It might not be with respect to x, but this is just a quick way to think about it. So you help me out here. What's the outside function? It's the square part, right? What's the inside function? It's the 3x squared minus 4. So let's try this. And there's two ways you can handle this. You can actually use u to do the problem. I can show you that, but I think you're going to like my method better in the end. Let me show you the u way of handling it first. So not this outside, inside first. What we were saying is that u is the inside. So I could write this as y equals u to the second power. Right? And u is equal to, you have to write it somewhere, 3x squared minus 4. You got to keep that in mind. So when I take the derivative of this thing, y primed is equal to, I'm using the power rule, so that's 2u to the times du, not to the, but times du. That's how you take the derivative of u with respect to x. You have to multiply it times du. Then you can go back and substitute in. All right, so that gives me y primed is equal to 2. Now, I should have made a bigger deal about that. You know, when you use the power rule, the 2 comes in front, you reduce that by 1, so that's to the first. I replace my u, so substitute 3x squared minus 4 times du. Du is, or du over dx, is the derivative of u with respect to x. I should put over dx, which is going to be the derivative of this guy. So use the power rule there as well. The 2 comes in front. That's going to be 6x. Reduce that exponent by 1, so it's to the first. And then minus a 0, because the derivative of 4 is 0. So there's our result. It should be simplified. So y primed is equal to, okay, now I need to distribute the 2 inside. I also have to distribute the 6x. I think it would be easier to just multiply those together first. That's 12x. Times 3x squared minus 4. Actually, there's absolutely nothing wrong with that result right there, because if you multiplied it out, it'd have a greatest common factor, which I've been telling you, it's really better to have greatest common factors factored out front. So that's the situation. Now, that does not use this cute little trick that I have written here for you. Let me show you that way. I think you're going to like that better when you start doing a bunch of these problems. So here we go. Y primed equals. Now we already established that the outside function is the square part and the inside function is 3x squared minus 4. So I say take the derivative of the outside. So that means power rule. Pull the 2 in front. Rewrite the inside. So that's going to be 3x squared minus 4 to the first power. That's how the power rule works. Times the derivative of the inside, which is going to be 6x minus 0. Now see how that gets you there just faster? So then I still do the same thing, multiply 2 times 6x, that's 12x times 3x squared minus 4. I think in the end that could potentially be more confusing, yet you're going to be happy you did it that way when you start doing problem after problem after problem, and you don't have to do what we call use substitution as we're doing above. But either way, whatever way makes you feel more comfortable, I think I'm going to stick to the way I did it in red here, the derivative of the outside, rewrite the inside times the derivative of the inside. So a second problem here, I want you to differentiate the function f of x as the cube root of 4x squared minus 6. Now, we're already in the habit of rewriting radicals as rational exponents. So this is a rewrite step. This is not taking the derivative. So this function is equivalent to f of x is equal to 4x squared minus 6 to the 1/3 power. Now I'm ready to take the derivative. And it turns out this problem works just like the last problem. The outside function is the 1/3, so we're going to use the power rule. And then the inside function is this polynomial 4x squared minus 6. So proper notation, f primed of x is equal to, remember power rule, move the 1/3 in front. Now when you do that, you should always rewrite the inside and then reduce that by 1. I'm going to go ahead and write it out, 1/3 minus 1. But don't forget, you have to multiply that times the derivative of the inside. So this 4x squared minus 6, the derivative of 4x squared, again, power rule, 2 times 4 is 8. That's going to be x to the first minus the derivative of 6 is 0. So this is power rule, rewrite the inside exactly the way it is. You don't take the derivative when you rewrite the inside. And then all of this is the derivative of the inside. Okay? After that, it's simplify. So I have f primed of x. And here's what I'm going to do. I'm going to multiply the 1/3 times the 8x. That's going to give me 8/3 x, or 8x over 3. And then I'm going to rewrite 4x squared minus 6 and simplify that exponent. We know 1/3 minus 1. If it helps, I could say that's 1/3 minus 3/3 when I find a common denominator. So it's going to give me an exponent of negative 2/3. I don't want to say there's anything wrong with this answer, but you want a functional derivative. You want a derivative you could use for something else if you need to. So this 4x squared minus 6 to the negative 2/3 needs to be moved to the denominator, so that negative is positive, and you could rewrite that in radical form. So f primed of x is equal to, that would leave me with an 8x in the numerator. That 3 is still in the denominator. That 4x squared minus 6 is to the positive 2/3 power now. I could even take that further and rewrite it in radical form. So this is 3. The 3 in the denominator of your exponent is the cubed root. And the 2 in the numerator means 4x squared minus 6 is squared. And this would be back in radical form, whereas this is not an inappropriate answer. It's just fine if your point is just to take the derivative and not use it for anything else, which we haven't used the derivative really for much else. Well, we've used it to find the slope of the tangent line, hadn't we? But there's more you can do with it. So let's continue our practice. We want to differentiate g of x equals 5 over 3x minus 5 to the 4th. Now when I'm looking at this, I'm thinking my outside function is raising it to the 4th power. But maybe we want to rewrite this first. You know, we talked about when you have your variable in the denominator raised to a power, really it's easier to use the power rule if it's in the numerator. You could use the quotient rule for this, but to me this is one of those rewrite problems. So that's what I'm going to do. You do not have to. You can use the quotient rule. Remember, low d high minus high d low over low squared. That would have been just fine. But you would be using the chain rule in the middle of the quotient rule, which could be an issue. So let's just rewrite this thing. This is g of x is equal to 5. And then I'm going to rewrite this as 3x minus 5 to the negative 4 power. And there we go. Now this looks like the last two problems we did. We have a polynomial as our inside function, and we have a power or an exponent as our outside function. So when I take the derivative, g primed of x, when I take the derivative of the outside, remember you multiply your exponent in front, so it's going to be negative 20. You rewrite the inside as is, and you reduce that exponent by 1. But don't forget, you still have to multiply times the derivative of the inside. What's the derivative of 3x minus 5? Well, the derivative of 3x is 3. The derivative of 5 is 0. So that is just 3 right there. When I simplify this, g primed of x, I can multiply the negative 20 in front times the positive 3 in the back. That'd be negative 60. And this 3x minus 5 is raised to the negative 5 power. Now, I'm not going to tell you that's a bad answer. It's not. But preferably, we would have all positive exponents in our final answer. So g primed of x is equal to, the negative 60 remains in the numerator, but the 3x minus 5, now to the positive 5, is in the denominator, and that is completely simplified. Now here's a fun problem for you. What do we have going on here? First thing, maybe you want to rewrite this function. So this is the rewrite step. So not y prime, just plain old y. 1/2 x squared. Remember, whenever we have radicals, we rewrite them as 16 minus x squared. And that's a square root, so that's to the 1/2 power. Now what you have here is a product. So we have to use the product rule. What do you mean by a product? Well, we're multiplying. 1/2 x squared is like our first factor, and 16 minus x squared to the 1/2 is like our second factor. So we're going to use the product rule, and in the middle of the product rule, we also have to use the chain rule. Okay? So this is where things get a little bit complicated, but you've got this. We can do this. So remember, the product rule says first times the derivative of the second, plus the second times the derivative of the first. It's been a few problems ago, hadn't it? So here we go. Now, again, let's keep in mind, this is your first. This guy right here is your second. So if I do first times the derivative of the second, I'm going to rewrite 1/2 x squared is my first. When I take the derivative of the second, I have to use the chain rule. So now I have to think about what's inside and what's outside. So my inside is this 16 minus x squared, while my outside is this 1/2 power. So power function there. Okay, so back to my green, I'm going to take the derivative of the outside. So that's 1/2. You rewrite the inside, 16 minus x squared, and reduce that exponent by 1. So I'm just going to write 1/2 minus 1. But don't forget, you still have to multiply that times the derivative of the inside. So the derivative of 16 is 0. The derivative of negative x squared using the power rule is going to be negative 2x. We're only halfway there, right? So what I have here is the first, and then all of this is the derivative of the second. Plus, now we're doing the second. So I'm rewriting the second function, which is 16 minus x squared to the 1/2 times the derivative of the first. So what's the derivative of 1/2 x squared? You move the 2 in front, so that's 2 times 1/2 times x to the first. So this is the second times the derivative of the first. Now that's our derivative, but man, it can use some simplifying, don't you think? So when I look at this, I've got some exponents to deal with right here that need simplifying. There's things that I can cancel. So here's the first thing I noticed right off the bat. One of these 1/2s, I'm going to go with this one, and we'll cancel with that. That still leaves me with a 1/2 x squared times a negative x. So I'm going to write that down. So I have y primed is equal to 1/2 oh, it's negative 1/2 too because of this negative. And then this x squared times this x is x to the third. And then I have 16 minus x squared. 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. So this looks better. Okay, now I'm moving over past the plus sign. Now right here, I have this 2 times 1/2. You probably saw that right off the bat a minute ago. And that leaves me with an x that I would rather write in the front. And then times 16 minus x squared to the 1/2. Now the following simplifying steps will really test your algebra skills. The more you practice this, the better you'll get. But I have some advice. Notice, think about these as two separate terms. So you have this negative 1/2 x to the third, 16 minus x squared to the negative 1/2, and then the second term x times 16 minus x squared to the positive 1/2. They both have a 16 minus x squared factor in common. Okay, so that should come out front. Something else, just advice, when you have a fraction in one of your terms and you're trying to factor out the greatest common factor, pull that fraction out front. So as I continue to simplify, I have y primed equals, oh, what else do they have in common? I just noticed they each have an x. So let's pull out a negative 1/2 x. Now here's where it gets weird. 16 minus x squared. Whenever you factor out common factors that have exponents, you always pull out the smaller of the two, right? That holds here as well. So that's negative 1/2. All of that's coming out front, folks. So this negative 1/2 is out front. One of these x's comes out, so that leaves x squared, correct? This 16 minus x squared to the negative 1/2 is already out. So all that's left in this first term is x squared. If you multiplied that back times this, you would get that back. You agree? Yes. Okay. Now, with this factor, this is where it gets a little weird. So watch this. I factored a negative 1/2 out of here. First of all, when you factor a negative out of a positive term, it turns negative, right? Now, I'm factoring a negative 1/2 out of a 1. Remember, a factoring step is dividing. So 1 divided by negative 1/2 is negative 2. Picture this. If you multiply the negative 1/2 back times the negative 2, that would give you that positive 1, right? Yes? Okay, good. Now, I pulled out 16 minus x squared to the negative 1/2. This is a division step. When you divide exponents, you subtract. 1/2 minus a negative 1/2 is 16 minus x squared to the first. I know the first time you see that, it's almost takes your breath. It's like, oh no, I have to do that. Yes, you need to do that. So there's some algebra there I need you to be thinking about. I need you to maybe pause the video and work this out in your head. I know you've got it. So again, what did I do? Fractions need to come out. Any common factors need to come out. So the x to the third and the x means x to the first can come out. The 16 minus x squared to the negative 1/2 and the 16 minus x squared to the positive 1/2. Again, the lowest of those exponents, which is negative 1/2, comes out. Then you do division. When it gets confusing, remember factoring is divide. So when I take that 1 that's in front of that x and divide it by negative 1/2, that gives me negative 2. When I divide 16 minus x squared to the positive 1/2 by 16 minus x squared to the negative 1/2, I'm subtracting exponents, so 1/2 minus the negative 1/2 is to the first. Now, believe it or not, that helps this problem. So I have y primed is equal to, in the front, I still have what I have. Negative 1/2 x 16 minus x squared to the negative 1/2. Here in the brackets can be simplified. That's x squared minus 32, right, plus 2x squared. I can add these x squareds together. So I continue to the right because I'm running out of space. I have negative 1/2 x 16 minus x squared to the negative 1/2 brackets. X squared plus 2x squared is 3x squared minus 32. Finally, this could look really nice by rewriting the 16 minus x squared to the negative 1/2 in the denominator. So in the numerator, I still have a negative. I have an x, so that's negative x parentheses 3x squared minus 32 divided by, denominator is 2. This goes to the denominator. Remember that exponent's a negative 1/2, which means it's a square root, and it's in the denominator. 16 minus x squared. Final answer down here. Y'all, it's the algebra. It's not the calculus. The algebra can get really sticky. You look this up as the answer, I would say, in the back of the book, or you're looking at an ebook online. When you look at this result, I do believe the one I have circled here is what you're going to see. So you would have no idea if you stopped up here if that's even right. You do have to go and simplify it. And keep in mind, you need a functional derivative. You need a derivative that you could set equal to some value and solve if that's what you have to do with it next. And in the next chapter you do. So what should we do about this one? Differentiate y equals x over the square root of x to the 4th plus 4. Now, rewrite always is my first step, seems like. Square roots are a no-go. We need to rewrite these. And so I'm going to rewrite this as x to the 4th plus 4 to the 1/2 power. Now, if you want to, you could take that x to the 4th plus 4 to the 1/2 to the numerator and make that a negative 1/2 and use the product rule. That really wasn't my intention on this problem. When you get to something like this, the product rule or the quotient rule, kind of either one, it doesn't matter a whole lot. I'm just going to stick with the quotient rule because it works just fine. So I have y prime equals, what is the quotient rule? Low-D high minus high-D low. So here we go, low, x to the 4th plus 4 to the 1/2. D high, what's the derivative of the numerator? 1, right? Minus high, which is just x, times the derivative of the low, d low, or the denominator. Now this is where you have to use the chain rule. When I take the derivative of x to the 4th plus 4 to the 1/2, I have to think about outside-inside stuff. The outside function is your 1/2. The inside function is your x to the 4th plus 4. Remember, you take the derivative of the outside first, so that's 1/2. You rewrite the inside, x to the 4th plus 4. Reduce that 1/2 by 1. That's going to make that a negative 1/2 times the derivative of the inside. What is the derivative of x to the 4th plus 4? Use the power rule. It's 4x to the 3rd plus 0, which is just 4x to the 3rd. And don't forget, this is over the denominator squared or low squared. So that's x to the 4th plus 4 to the 1/2. That whole thing is squared. That's your derivative, right? That's it. But simplifying is required next. Okay, so here I go. Y primed equals, now this x to the 4th plus 4 to the 1/2 times 1, I'm just going to rewrite that as x to the 4th plus 4 to the 1/2. And then minus. And here's some things I see. There is no distributing these factors into this because that's raised to the negative 1/2. We'll deal with that in a minute. Okay? But I can cancel this 2 in the denominator with this 4, and that leaves 2. And then I can also go ahead and multiply this negative x times this 2x to the 3rd. So that's negative 2x to the 4th. And then I have this x to the 4th plus 4 to the negative 1/2 over denominator, this 1/2 times this 2. Remember, power to a power you multiply just gives me x to the 4th plus 4 down there in the denominator. Next, we get to practice that step that we did a few minutes ago, where notice they both have x to the 4th plus 4s. One's to the plus 1/2, one's to the minus 1/2. What do? You factor out the least of those. So I'm going to factor out x to the 4th plus 4 to the negative 1/2. That's going to leave me with, well, I'm not pulling that out. I'm pulling out a negative 1/2, right? That's a division step. So 1/2 minus a negative 1/2 is going to give me 1, right? That's going to give me x to the 4th plus 4 to the 1st power. That's probably the biggest algebra step that gets folks. So again, you pull out the smaller of the two, which is the negative 1/2, and then you're dividing. So x to the 4th plus 4 to the 1/2 divided by x to the 4th plus 4 to the negative 1/2. You subtract exponents, and that gives you the 1. Minus, okay, 2x to the 4th, and that whole term has already, or factor has already moved out front. And that's divided by x to the 4th plus 4, that's to the 1st. So the parentheses are not really required in the denominator. Now, I'm going to scoot on over. I need room. So I'm going to scoot on over. And I still have this out front now, I guess to save us a little bit of space. What I'm going to do is move this guy right here to the bottom. What happens when I move him to the bottom? That changes to a plus, right? That's going to turn into a plus 1/2 down there. So I'm going to write that down so you can see what comes after that. Now in the numerator, check this out. I've got an x to the 4th minus a 2x to the 4th. So in the numerator, I have 4 minus x to the 4th. Do you agree? Because this 4 is still there. And then x to the 4th minus 2x to the 4th is minus 1x to the 4th. So that's that. And in the denominator, I have x to the 4th plus 4 now to the positive 1/2 times x to the 4th plus 4. Remember, that was raised to the 1st. Well, these are the same factor, so that means I can add these exponents. So the best looking answer we can do is 4 minus x to the 4th over x to the 4th plus 4, and 1/2 plus 1 is 1/2 plus 2 over 2, which is 3/2. Simplifying takes practice, a lot of practice. When you're dealing with chain rule in the middle of a quotient rule or a product rule, there's always some algebra to do. Y'all, I'm going to wrap up part 1 right here, and then I'm going to show you, the next video should be on the shorter side. I've got 5 more slides to go over with several practice problems. So come on back for part 2 of the chain rule.